thank you for invitation. It's been, I can tell you, I've been, when did we meet? Back in over like 15, almost 2 decades. So, since then, we had a lot of PowerPoint slides and things like this. And, time flies. And now I can show you some of the beautiful hardware we're developing and also some of the missions we are part of. But before I start talking about exploration, I want to give you a glimpse of of a company that sort of Charlie mentioned earlier. We started in Manhattan, right on 34th Street and 9th Avenue. So this was our office for a decade. Prior to that, Little Italy. And at one stage of a decade ago, we decided to move to venture west. I moved to Los Angeles and started the Altadena office, and my colleague moved to Denver to start the Longmont office. Since then, we have grown, and we are close to 300 employees. So when I met Charlie, we were 30 people, and now we are 10 times bigger. So things definitely improving in terms of space exploration and funding for space. So we have two divisions: motion control in Longmont and the exploration systems in Altadena. The exploration systems, what do we do? Well, we design these so-called space mining robots. Robots that go out to space and we touch the soil. They drill, they dig for two purposes. The first one is to sustain human presence, so for in situ resource utilization. And the prior speaker mentioned MOXIE, so this is the first step in the ISRU. And another reason for building space mining robots is to find life in our solar system. So we call it touch life. And pretty much all the systems that we're building fall into these two categories: touch life or mine the sky. Pictured on the bottom are the missions we are involved with. So here you have a Dragonfly. We're building mining system that will capture Titan material at 94 Kelvin ice and deliver to the instruments. We have a few things on the Perseverance rover. But the blue asterisk is something that I'll talk about more. So that's Viper rover that will explore the moon in a few years. We are also building tools for astronauts. All these power tools to drill down, a couple of meters, capture regolith core, capture rock samples, perform geotechnical studies, and so on. And the far right is Phobos. We are building mining system that will grab material from Phobos. And obviously, Phobos, it captures a lot of Martian materials as well. So it's not going to be just Phobos material. It will also be Martian material. So we'll capture this material and return back and to Earth. And this is part of the actually Japanese mission called Martian Moons Exploration that will launch in 2004. And at the same time, as we go through the missions, we also have a funnel of around 30, 40 R&D projects. And these projects are the technology is slowly being maturated until they become mature enough to be infused into flight mission. And the blue asterisk over here is Redwater. This is ISRU system, and I'll talk about it. What you see here is so it looks like a Darth Vader hat, but it's a pneumatic sampler for a comet sample return mission called CESAR, with a goal of bringing at least 100 grams of comet material. Then right over here with another blue asterisk, we have a Cryobot and Slash. This is the nuclear-powered drill that will penetrate through Europa ice and get down to the oceans and do exploration and hopefully find life. So exciting stuff. If you ever in Los Angeles, please look me up and I'll give you a tour. We open June 15th. Entire California opens. That's my sort of office. This picture is actually pretty old. We are over 100 people right now. The gambit of engineering disciplines. Most of these 100 people are pretty much engineers, and we also have PM and mission purchasing, administration, and so on. We not just do on lab engineering. We also go out to the field, and the slides that I'll show you will give you a glimpse of a field experience. And the field experience is extremely important because we get to see how the hardware performs in its natural setting, as opposed to perfect laboratory setting. And it's very, very different. The building on the right-hand side, it used to be Walmart, one of these neighborhood Walmarts a couple of years ago. We took it over, got renovated it, and designed it to build robots. We spent probably 6 months planning out all the aspects of what we do to make sure that facilities will support it. So we have area that's extremely dirty. You go in, it's a geotechnical lab. You go in, it's dust all over you, and then we have area that's extremely pristine clean. So you have this person standing in a gown with goggles, with masks, and that's pre-COVID. All right, that's pre-COVID, and it's sitting inside a clean room, and just behind this person you have so-called vacuum oven. This is where we cook our hardware at 350 centigrade, and then using sterilized tools assemble it. It's so clean. There are few things that are cleaner than the hardware that we're putting in this particular facility. All right, let's talk about, first, I'm gonna give you 3 sort of chapters about 3 different technologies. And the first one is gonna focus on searching for water on the moon. As you know, moon has water, and it's not just water, it's also carbon dioxide, carbon monoxide, ammonia. So if you sort of take water or volatiles from a moon and you try to drink it, it's a poison, right? It's poison. You have to really clean it up. So how did the water got there? Well, there are a couple of theories, but the obvious ones is comets and asteroids. And some folks think that asteroids was main source of water on the moon. And water got in, and then water molecules would hop on the surface of the moon during day-night cycles. And every so often, one of the molecules would hop into what we call PSR, or permanently shallow regions. Those regions are in the North Pole and in the South Pole, in a deep craters. So when sun is shining, these craters are so deep, and they involve north and south, that no light is getting inside. And temperature inside those PSRs goes down to around 40 Kelvin. In fact, this PSR is one of the coldest, if not the coldest, region in our solar system. Comets don't go down to 40 Kelvin. Titan, by Saturn is around 94 Kelvin, and PSR so close to the moon, to the sun, yet it's the coldest place on Earth, in the solar system, just because the sun is not reaching it. So once these water molecules hop in, they stay there. They don't have energy to come out. It's sort of like in ice accumulation in a freezer. Once water molecule sticks onto your freezer, it stays, and the ice slowly accumulates. And that's exactly what happened in those PSRs. So our job is to go there. Why would we go and do all the mining? Well, it's to, frankly, cut down on the cost of exploration. It's to become more efficient to explore space. The water that we would mine on the moon would be essentially gas stations on the moon. On the picture is a Blue Moon lander from Blue Origin with the big tanks, and to come back to Earth, you don't necessarily need to bring a fuel with you like done during Apollo. you can extract water from these PSRs, break it down into liquid oxygen, liquid hydrogen, and come back. The same water can be used to sustain human presence on the surface of the moon. So it's essentially cost driven, making sure that our exploration is as efficient as it can be. Very first mission that will go and touch this icy soil is called Viper. It's essentially a resource prospector mission. It will drive for 100 days, and there are a few instances where it's going to be actually pitch black at night. It has several instruments. Neutron spectrometer is mounted right in front. Neutron spectrometer sniffs for water, for hydrogen, and hydrogen is a proxy for water. So it drives around and sniffs. And if it sees high concentration of hydrogen, we'll stop and we'll deploy the drilling system. The job of a drill is to go at least 1 meter down and bring chips to the surface for analysis by two other instruments. The first one is called near-infrared spectrometer, or NIRVAS. Its job is to look for the content of volatiles and also mineral content. And then we have mass spectrometer, or M-SOLO, that's looking for different volatiles, whether it's water or whether it's CO, CO2, and so on. And at the end of the day, you can see there is a temperature map on the bottom right-hand side. There are similar maps with water concentration, but the pixels are very, very big, of the order of kilometers. So idea is to do exploration in a micro scale. Look at what's a spatial resolution, at the very low spatial resolution of three-dimensional spatial resolution, going meter down and a couple of kilometers across. This is our drill, and right now, as we speak, we have a hardware coming into our lab where we're going to assemble this entire drilling system. It has it's a 1 meter system, but the entire length from the top to the bottom is around 1.5 meters. It has rotor percussive drill head right on top. It's a hammer drill. It's a percussive drill. And if you ever look out on the outside, look at the construction workers, they have these so-called pavement breakers, right? And they don't even push on this tool. The tool with the percussion that does all the work of breaking out concrete. And that's why we incorporated percussion into our drill. So if the ice or icy soil is extremely hard, and it's like hard as concrete, we're gonna turn on percussion. It's gonna go pick, 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 and break up the material. And then the other important aspects is this auger with a screw. It's not a uniform. Right at the bottom, you have a bite section that has very shallow pitch and very, very deep. This is designed to capture the material. And as we capture the material and we pull the auger up, you can see the brush that brushes off material onto the so-called cutting stone. It took quite a bit to develop this system. We actually started lunar drill development back in 2004, and the funding would come on and off, on and off. So it's a really a career to put something together like mining system. This is a close-up of a drill on the picture to the right-hand side with a brushing station. And we incorporating so-called a bite sampling routine. So we drill 10 centimeters, we pull out, we brush off material onto the cone to be analyzed by the two instruments, NIRVAS and the M-SOLO. And then we go back, we capture another bite, we pull out and we dump it. The pictures at the bottom show the accumulation of these cones in 10 centimeter bites. And we did it for a reason. As you drill down, you don't want to put too much power into the subsurface. So going down and pulling out, dumping the cuttings, going down, pulling down, dumping the cuttings, it's more efficient way than going all the way down and excavate the cuttings through 1 meter length of auger onto the surface. Second, our requirement is to keep stratigraphy preserved. So we're preserving stratigraphy in those 10 centimeter bites. So we go down 10 centimeters, we pull out, and the two instruments, we analyze the sample from this 10 centimeters. So that's how we know how the what lies below the surface. And as I mentioned, testing is really important, and analog testing is extremely important. We went to Antarctica. We went to a place called Dry Valleys of Antarctica. Those dry valleys, they call dry because no liquid water has been present. So all the water, you can see glacier, right? This white patch, it's a glacier. What the liquid posted out of atmosphere, just like on the moon, these was also vapor deposited. So it's a really good analog, not just for Mars, but also for the moon to some extent. To get there, first we fly to McMurdo Station, and right in that bottom left-hand corner, this is Scott's house. Scott wintered over a couple of times, and all the supplies he left, they're still there. It's essentially a museum. It's well preserved. You fly in one of these airplanes, but you land on ice, and then you stick around in these buildings and facilities for 1 to 2 weeks to gather all your gear to make sure that you have everything: food, water, propane, plus your hardware that you want to test. And afterwards, you hop on a B-212 helicopters, and they drop you off. They never stop rotating. They drop you off, and they fly away. And then you're out there in the middle of nowhere, for a week, 2 weeks, a month at a time. So first thing is you need to establish a camp. So if the weather changes, you can actually hunker down and survive adverse weather conditions. And once all the supplies, everything is arranged, at that point you start doing what you're supposed to do, with science or drilling. In this case, we put our prototype drill, and you can see this glacier right over here. We put the prototype drill, and then we start drilling down in these so-called bites into the subsurface. And what we found is the top layer is relatively dry. It's probably 10 centimeters. And then below this, you hit ice cemented ground. And this ice cemented ground, it's just like ice cemented anywhere else, Alaska or East Coast in winter. Over here, it's vapor infused that created this ice cemented ground. In Alaska or on the East Coast or Canada in winter, it's the water coming down and refreezing. So end result is exactly the same, but the mechanism, how you got there, is different. So what we found is, as you drill down and you excavate this icy soil, if you keep it extremely cold, it behaves like sand, dry sand on the beach. It's only when you warm up, it's gonna start sticking and it turns into a mud and so on. So it's extremely important to make sure that you don't put in the heat into the subsurface during drilling. And we also have a temperature sensor right at the bed to measure temperature while we're drilling. And if temperature goes up a little bit, we stop, you pull out, we wait until things cool down, and we go back into the same hole, and then we carry on drilling. So it was just great experience. We found different drilling modes. We found different sampling modes. At the same time, we also had a lot of fun. It's absolutely pristine environment. It's beautiful. It's quiet. It's really adventure. It's really an adventure. All right, now let's switch gear and look for talk about searching for life. Life requires three ingredients. It's water, it's chemistry, and it's energy. If you have all of those three, doesn't mean you're gonna get life, but it means that you can start looking for life. If energy is not there, don't look. If chemistry is not there, you don't have right elements, don't look. If there is no water, don't look, right? You need all of those three to stand possibility of creating life. There are, apart from Earth, which has plenty of water and energy and obviously chemistry and obviously life, there are other planetary bodies which we call ocean worlds. These planetary bodies have actually a lot of water and you know, as a liquid water. Europa, for example, is a size of our moon. It's the size of the moon, and right at the bottom, I've got a table: moon, diameter of the moon, and diameter of Europa. You can see it's pretty much the same, but it has more water than our planet Earth. Okay, you can see these water bubbles. Can you imagine a planetary, moon the size of our moon having more water than Earth? So it's just incredible. Europa also has chemistry and right elements, and it also has energy. So it has this crusty, icy layer, 10, 15, 20 kilometers thick, and then it has liquid ocean. And there are many other ocean worlds out there, but Europa is most interesting. So here is a video from NASA Jet Propulsion Lab. We are part of the cryobot team that's developing a mission to Europa 20 or 30 years from now. So this is surface of Europa. It's very cracked. It sort of looks like a scan because of a tidal expansion and contraction coming from Jupiter itself. This layer that you see of ice is around 10, 15, 20 kilometers deep, and then underneath you saw ice. So what you see is a lander with a probe right on top. The lander has a couple of RTGs, or radioisotope thermal generators. These are the plutonium-based power sources, very similar to what Curiosity has and Perseverance has. So when we touch down, we are preloading so-called a launch tube that kind of melts down and vaporizes down, forms a seal. Once you form a seal, then cryobot is being lowered down, and you can see it starts rotating, and it slowly starts going below the surface. Cryobot has a couple of things. Got this rotating drill bit that mechanically cuts through ice, and also has a heater zone to warm up at the same time. So what you see is these so-called, we call them hockey pucks. These are communication hockey pucks that send the data right through the column of ice to the lander. But all the data processing, all the instrumentations, analysis is done on board of the probe itself. When we find something interesting, we are communicating back through these RF hockey pucks to the lander. The probe is designed with its own power source. It's also either RTG based or nuclear based. For two reasons. First one, it keeps itself warm, and ice on the outside, it's around 100 Kelvin right at the beginning. So it keeps itself warm, and this heat is also used to generate electrical power to rotate the bed, to run computers, to run instrumentations. Once we cut through ice, we reach the bottom, then the payload bay opens up, and voila, we have a rover. Yeah, you can have an underwater rover that has actually positive buoyancy. And this rover, if it wasn't for this ice, it would float all the way to the surface. But because of this low buoyancy, it presses against the bottom of the ice, and by doing so, it can traverse. So it's a upside down rover really that drives around on the ice and looks for for certain features, and it also has instruments. It has this umbilical connected to to the mothership. And whenever it finds something, it sends the data back and sends information. So very exciting mission. It's probably going to happen 20 years from now. It's a lot of things that have to be developed. It's magnificent exploration. So as I mentioned, testing. So we built a prototype of this deep drill. It's pictured on the right-hand side. This one is actually 5 meters long, 4 inches in diameter. And the first thing was to test it in a gypsum quarry, just to see how it is cutting through gypsum, which has a strength of around 30 MPa, which is close to the strength of ice. And we drilled down a couple of meters. We had the instrument right on top. This instrument is a deep UV Raman spectrometer called Watson that's looking for live signatures, for biomarkers, for organics. And this picture right over here is picture taken from this instrument, and you can see the light. This is a couple of LEDs shining onto the borehole. These LEDs tend to fluoresce if there is any organic material that fluoresces. It sends the light back, and we capture this image. And when we look at the frequency, and frequency tells us what sort of organisms live below the ground. So that's in gypsum. And obviously, if we're going to ice, we have to go to the summit, right in the center of Greenland. To get there, you fly to actually Denmark, and then from Denmark, from Copenhagen, you fly to a place called Kanga, or Kangerlussuaq. This is right on the edge of a glacier, and it's actually becoming a big tourist attraction. A lot of ecotourism. People come during summer, and we venture onto the ice and into the surrounding areas. So we sticked around there for a couple of days, and then we went on a plane, on an Air Force Hercules, all the way to the summit, right in the center of Greenland. And you land here on the skids. Then you have probably like an hour to remove all your gear, all your stuff. And fortunately, you don't need to camp by these permanent, semi-permanent houses, and they're sitting on stilts because the ice moves. This ice floats, and ice accumulates at the rate of meter per year. So every so often they have to bring brick trucks and either jack this thing up or move it to the side. But it's a lot of work to raise, around 15 people during summer and during winter, upkeeping this entire campsite and the entire base. So that's where we have internet, food. That's where we do meetings, and then it used to be tents, but the polar bear came out 2 years ago, and since then there are no tents. We sleep in a fishing huts. So once we have everything set up, then we venture out to away from the summit. So summit station is right over here. You can barely see it through a bit of a fog, and you try to establish your campsite for drilling. So this is our warm tent. That's where we have a kitchen and the supplies and everything else, and we are obviously driving on a skidoos and bringing all these supplies. You have a generator sitting right over here, and we put all these flags because whenever the weather comes in, and the flag is the only thing that you may be able to see. The next thing was to dig a deep trench, and the reason for that was to get down where it's even colder and establish the drill base. So this is part of the drilling system, and this is part of our drill tent, and this is fuel right over here. And then we had to put the tent over the drill. So fortunately, there was no wind. We took the tent up, and idea was to put this top of a drill through this hole right over here in a tent. And if there was wind, I mean, this looks like a parachute, right? If there was wind, this thing would be gone. So we were worried how we gonna how we gonna assemble this entire base. But fortunately, there was no wind that day, and we took it and put it up, and voila, we have a drill tent. And what you see is our drill operator setting up computers. This was fully autonomous drilling. So he wants to make sure that everything works, computers works, electronics works, the winch works, and that's our drill. And the hole is right underneath the drill, and you can see a bit of a deeper trench. This is where we were capturing all the core samples. And this is a final core that we captured. It's around 30 meters. We drilled all the way down to 110 meters, but we captured core from 70 to 110. And the bottom of the core, we took some of this, we melted, and we drank it. And this, as you go deep, you go back in time, and the water we drank actually was hot chocolate made with some of this ice. Was created when Christopher Columbus arrived in America. So a few hundred years old, and the rest of the core was taken and analyzed for for microbes, and we did other science experiment with it. But again, great adventure. We learned a lot how the drill behaves in ice, what sort of drilling protocols we need to employ to actually drill and not get stuck. Once if you get stuck below the ground, that's it. You have to wait for for climate change and global warming before you can retrieve it. It's gonna be there forever. So it was a lot of fun. And finally, I want to talk about human exploration. I still have, I believe, 10, 15 minutes. So I want to talk a bit about human exploration and what we do to sustain human exploration on the surface of Mars. The SpaceX and obviously NASA have been looking very carefully where to send humans to Mars. And to do this, there are a couple of criteria that you have to meet. First one, you have to be lower down in elevation to give yourselves more time to slow down through atmosphere. So you want more atmosphere to slow you down, so you have to have a lower elevation. So that's why if you look at where we landed in above equator, where elevation is down, below equator elevation is up, so you don't have as much time to slow down. We also need to be lower than 40 degrees latitude to take advantage of sun. More sun, obviously more power. We don't want to land where you have rocks, so we have to look at the rock-free area. We also need to look where the slopes are less than 5 degrees. And we need, obviously, finally, locations within the proximity of water. Arcadia Planitia, in fact, is one of the sites that meets all those criteria. And that's where we want to go, and that's where we want to mine water. And below, there are regions within Arcadia Planitia where you have maybe 10 meters of dirt, followed by 100 meters of ice. So as you can drill down and into the ice, capture the ice, melt it, and use it for fuel and sustaining human presence. So what we are building right now is a system called Red Water. Red Water uses technologies that we borrowed from terrestrial applications. The first one is Rodwell or Rodriguez well. This is a way of mining water in the South Pole to sustain the human presence in the South Pole. What it is essentially a pipe that goes down, and with a melt probe. This melt probe melts ice, and you have a pump that pumps water to the surface. It's relatively simple. And then this is this is a drilling system that uses, as opposed to these, traditional drill pipes, it uses a hose. It's it's like 2-inch, 3-inch metal hose that goes down through something called injector, which deforms it into a straight pipe. And at the bottom of this injector, you have a bottom hole assembly or drill bit with drilling motors and everything else. And to drill down, you essentially unspool this drill, you go down, you use mud in case of terrestrial applications or compressed gas in case of Mars application to drill down. So here, this is our red water. You have this hose. It's around 1.5 inch that goes down with through the injector with bottom hole assembly, drills down through 10 meters of dirt, gets into the ice, melts it, and pumps it to the surface. So the previous speaker mentioned MOXIE, and MOXIE uses a compressor to compress Martian atmosphere, and this is one of the subsystems we would use for red water to compress Martian atmosphere and create this high pressure gas for drilling. The operations would be relatively simple. We have a gas supply from MOXIE. We drill down into the ice and we blow the cuttings out of the hole like in traditional drilling. And you can see the bottom hole assembly with a drill bit. Once we're in ice and we have a nice, nice hole, we expand this packet system and we pressurize the borehole. Once the borehole is pressurized, we spin and we start heating. The bottom hole assembly has a couple of kilowatts of power of heaters, and we create this melt pool. And then we pressurize a little bit more. We open a gas valve, and the water under pressure flows to the surface and to the tank, sort of like a geyser in Yellowstone. So this is our prototype system. You can see the cold tubing sits right over here through injector, which has a bunch of pulleys and the drivers, and this is bottom hole assembly, which has all the motors and drill bits and tubing required to do all the drilling. This entire system weighs 66 kilograms, so it's not very heavy. In fact, it's something that Curiosity or Perseverance size rover should be able to deploy it. And then when you do the close-up, here you can see a couple of these pulley systems. One of them is a driver that makes sure that pulls the tubing and deforms the tubing into the straight pipe. And you can see these friction teeth. So this tube is smooth, right? But when you pull it out, our gears, our pulleys have a teeth that kind of bite in, deform the metal, and pull it down. You need around 1 kilowatt of power to actually do this. It's a very slow motion, high torque, and it works. It actually works pretty well. This is our setup inside the freezer. We have a 5.5 meter freezer with gantry system, and this is scaffolding. That's our red water cold tubing system, and we had something like 1.5 meter of ice, these ice blocks. So we had to put each of these ice blocks is like $200. You buy it, they deliver it, and then we essentially glue them on top of each other, forming this this column, and that's our bottom hole assembly. It takes actually quite a bit of time to put this test together. It took us like 3 weeks to assemble everything before we were ready for testing. And that's formation of a melt pool. We put actually a dye to make sure that the water is red, because the project is called Red Water, and you can see how it slowly forms into this melt pool. And on the right hand side, you can see the drill going all the way to the cold tubing right on top. So this was end-to-end demonstration of essentially drilling down and melting and then pumping to the surface. But this was done in a freezer. And the end game is to actually test it in the Mars chamber. So to do this, we had this 3.5-meter Mars chamber with a cold tubing sitting right on top, with an injector system and a drum with ice. So this is actual setup, and cold tubing right here and the bottom hole assembly with a lot of wires, a lot of cameras, a lot of thermocouples, and you can see a lot of tubes, a lot of electronics. It's again took almost a month to set it up, and we managed to drill down. So we drilled down, we stopped, we melted it, and we pumped water to the surface. So you can see this. It's sort of to us now, it's a familiar shape of a melt pool. What the guys did, they took this drum out after experiment, and they cut it open with a chainsaw. And what happens is this melt pool is not cylindrical; it's a sort of conical in nature, because the warm water actually starts flowing to the top and starts melting also up. So it's up and not just down. So you're getting this this cone of a melt pool. And we are busy right now developing next generation system that will have it's a technology readiness level 6. It's going to be flight-like, with enough cold tubing for 20 plus meter of penetration, with this nice looking injector, the tubing and the bottom hole assembly that's watertight and so on. And for for scale, we put an astronaut here right next to the system, and all of this is mounted on an athlete, JPL's athlete rover. So you have a water storage tank, and you have a gas supply tank with compressed air, and the compressor is essentially a Moxie compressor. And I forgot to mention, but actually Moxie is powered by electric motor that Honeybee has developed. So this compressor is run by motor that our division in Longmont has built. So we have a part of ISRU system on Mars. So it's very, very exciting. So I want to thank everyone for listening, and maybe a couple of questions. This picture was taken in a summit in Greenland. So I'm standing actually right over here, and this is during the time where we were digging the hole. It was extremely cold. You can see actually flag post. It was pretty windy. So during this time, we didn't have to put the tent on top, but it was good to actually dig the hole and get everything lined up. But you can see very, very foggy. If fog comes in, you lose visibility in no time. So we always had to watch out for where things are. And then we had to put these flags every so often in ice to allow us to actually get back into the base camp, into the summit. So I've got probably a few minutes left for any questions, if there are any, but otherwise happy to entertain Q&A or entertain some discussions. Thanks, everyone.